Let's say you had a solution of some amino acid and you had no idea what it was, but you wanted to find out. And so one of the common techniques that we'll turn to in lab is NMR analysis, nuclear magnetic resonance. And so what we do is we're going to rely on the different environments that all of the protons exist in on a biomolecule, for instance, and how that is unique, and that helps us identify a particular biomolecule. And so what I'll do in this video is go over how we can look at something like valine or just from the nuclear magnetic resonance spectra, be able to deduce what amino acid you're looking at. In this case, I'll be examining valine, and then also introduce some cool concepts that allow us to determine kinetic parameters. And so to begin with, after you've put your solution into the NMR machine, you've run the spectra, you get something that looks like this. We've got this ppm value, a chemical shift, denoting our x-axis, and I should write better. And this y-axis is kind of arbitrary units that just denote intensity. And this is one form of an NMR spectra. The main thing we're looking at here is the chemical shift values for each one of these peaks. But commonly, you'll see peaks that look like much broader, and they'll have actual areas. And these areas will tell us what number of protons we're dealing with by normalizing these peak areas to the total area of the peaks of interest. And so the first thing I like to do in analyzing a spectra is label the peaks. And so working backwards or downfield, I'll call these peaks A, B, C, D, and E. And what we'll note here is that at a 0 value for delta, our chemical shift, that is equivalent to TMS. And TMS is a very similar proton environment to methane. And what's special about methane and TMS is these protons that exist in those kinds of environments are very shielded. They have a lot of electron density around them, and consequently it requires more energy to flip these protons between their spin states. And so the more de-shielded a proton is, the farther downfield it will appear. And so that is a very key thing to keep in mind when you're analyzing NMR spectra. And so the first peak we're going to come across is peak A. And peak A is very close to methane and TMS signal. And what we'll note here is if we just eyeball this molecule, we're going to note that we have the presence of these two methyl groups sticking off our beta or gamma carbon in valine. And these two sets of 3 protons are very similar to it, and that's how we know to assign these peaks to A. The next peak that we come across, peak B, we'll note how nitrogen is somewhat close to carbon on the periodic table of elements, and so because of that they have relatively similar electronegativity values. If anything, nitrogen is a little bit less electronegative than carbon, and so peak B, this amino group, will be what we find coming up next. And then peak C is the next peak we'll come across, and the way it generally works is you can use your intuition to an extent. When we start getting peaks very close together like this, you really need to memorize and look to tables to determine this stuff. So we've got these terminal methyl groups here. Terminal methyl groups off a secondary or primary carbon are going to be very shielded relative to, for instance, like a tertiary terminal methyl group. And so being able to use your intuition, it's a mixture of intuition and memorization, but continuing, what we would find is the next peak that we'll come across that's farther downfield from methane and TMS is this peak D, which would correspond to this guy. And the reason you'll note, why is D farther downfield? Well, it's getting very close to these oxygens, and oxygen is one of the most electronegative elements, as well as this nitrogen group, which can also sometimes withdraw electrons from it. And so this proton here is experiencing a partial positive charge that is a lot greater than these terminal methyl groups, for instance, and because of that, we're seeing it farther downfield. And then finally, if we've got a proton right next to an oxygen, one of the most electronegative elements, we're going to find it very far down here. And a big reason for that also has to do with the fact that these carboxylic acids are able to form resonance structures quite easily. But it's suffice it to say, this proton is extremely de-shielded, and consequently it is very easy to shift or move the proton from its alpha to beta spin state and vice versa. So we see it all the way down here. And so this concludes a general introduction on the how we can use NMR to analyze amino acids. If you look at the other amino acids, they will all have unique NMR spectra. And so if you have a photographic memory, or we can turn to computers, if you know you only have one amino acid in your solution, or any, we can be able to figure out which amino acids are present via this kind of analysis. And so I'll follow up with a video on how we can determine kinetics with this stuff if we introduce deuterium. Or we can also use other things to deduce structures such as the nuclear Overhauser effect, which sounds a lot more complicated than it is, but I'll get to it. And so I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.